Hello, everybody. Hey, we have a little follow-up to week 4, lecture 1, and this is going to be week 4, lecture 2. Now, this is a follow-up on uniform circular motion. And as we discussed in uniform circular motion, we are going to have a centripetal acceleration that is equal to v squared over r. So if I have this one right here going around, okay, and I, for example, want to calculate, what its centripetal acceleration is, okay, I'm going to measure this, and it is going to be 60 centimeters long. And if it is rotating, okay, at 90 RPM, 90 RPM. So again, we have a radius that is equal to 0.6 meters, and we have a rotational velocity. We'll talk more about that later, okay? But that is going to be 90 revolution per minute, RPM. Okay, so first of all, what is the velocity? And second of all, what is going to be our centripetal acceleration? Okay, so if we have 90 revolutions in 1 minute, okay, we are going to have a quick dimensional analysis. And for every 1 revolution, you're going to have 2 pi r, and our radius is 0.6 meters. And for every 1 minute, we're going to have 60 seconds. And by a quick calculation, we are going to have 90 times 2 times pi times 0.6 divided by 60, and we're going to get 5.65 meters per second. 5.65 meters per second is going to be our velocity. So if we now want to calculate our centripetal acceleration, then we're going to have 5.65 squared divided by 0.6 divided by 0.6. And we're going to get 53, and that is going to give us 53 meters per second squared, and that is our centripetal acceleration. Now, if that was the only acceleration, then we would have something that would be going in a circle. So, and that is the uniform circular motion. So if our velocity here, okay, stays the same magnitude, right? Now it's obviously changing direction, so it's not a constant velocity, but it has a constant speed. Okay, so if it only has centripetal acceleration, that would be going towards the center. And it would just keep going in a circle. Well, what if it also had, okay, what if we also had a tangential acceleration? If we had a tangential acceleration, then it would be moving in essentially 2 directions at once. It would be accelerating in that direction. Okay, so let's say that we had a centripetal acceleration that was equal to, we have our centripetal acceleration that is equal to 53. Well, what if we had some sort of rocket on some object here, and it had an acceleration of, let's say, 15 meters per second squared, okay, then what would the overall acceleration be? And really what we have here is we just have a right triangle, and we can make this the right triangle, and then this down here is our tangential acceleration. Now we could also do it here, and either one of these triangles here. So in this triangle, we can calculate what the hypotenuse is by using Pythagorean theorem, which is going to be the square root of 15 squared plus 53 squared. And that is going to be sorry, I messed that up. 53 squared plus 15 squared equals, that would be 55, okay? So we would have this overall acceleration, which is the square root of the centripetal acceleration squared plus the tangential acceleration squared, would equal to, in this case, 55 meters per second squared. Okay, but what direction? What direction would that be? And now we're just going to use a little trig, and we're going to say the inverse tangent of opposite over adjacent. So we can go 15 over 53, and inverse tangent of 15 divided by 53. That's going to give us 15.8. So we'll call it about 16 degrees. Well, now, is that 16 degrees? Is it this angle or is it that angle? Okay, and we can see that if it's this angle, our opposite was the 15 and our adjacent was the 53. So this angle right here, 16 degrees, that is with respect to what? And then we could say with respect to the radius, which would tell us that that angle is measured going towards the center. So, well, we could obviously also change that, and we could say, we could describe this angle here, okay? Well, that angle there is going to be 84 degrees. So we could say that this was 84 degrees with respect to the tangent. Okay, so we could say with respect to the tangent of the circle. Okay, so when we get a two things that are going to go on like that, we could have a circle that's going to do something like this, right? So it's not that curve, not a circle, but that curve, sorry, is not going to have a constant acceleration because it keeps getting more and more and more. Okay, so if we started out with this as the radius 1, and then this is radius 2, and then that is radius 3, these radiuses keep getting bigger and bigger and bigger because tangentially there's an acceleration. Okay, so whenever you have any sort of curved path, that does not continue in a circle, you're going to have two components. You're going to have the centripetal acceleration, which is making it go towards the center, and you're also going to have a tangential component, which means it's not going to double back. And this obviously happens all the time. Anytime you have anything that is not moving in a circle, any sort of curved path, there's going to be some force that is causing it to go perpendicularly. and that perpendicularity is going to be either a centripetal acceleration or a tangential acceleration, depending on your perspective. Okay, now I've put in some questions into this week 4 problem set 1, which you will see, but a lot of that just has to do with using Pythagorean theorem and the inverse tangent to calculate those things. And we're going to do one more example here, and we're going to move on to relative velocity. Okay, so what happens if we have a race car and its initial velocity is equal to 0 and its final velocity, let's say, is equal to 30 meters per second, and we have a radius of 200 meters, and this race car is going to travel in that distance in, let's say, our time is going to equal to 5 seconds. Okay, 5 seconds. What is the total acceleration? Total acceleration of that car. So we're going to have to do 2 components here. We're going to have to do the linear, or the tangential, and the linear. Okay, so the velocity is obviously here at 0 and here is 30. So what I want to know is, we're going to say, what is the total acceleration here at the end of that curve? Okay, so the centripetal acceleration is the easiest one there, because we are already describing that as 30 meters per second, and then that gets squared, and then we're going to divide that by 200. So 30 squared is 900, divided by 200 would give us 4.5. So our centripetal acceleration is 4.5 meters per second squared. Now, obviously, that is going towards the center. Now, the way to determine what the tangential acceleration is think of this curve. Think of this curve as just a flat line, okay? And then, so this distance right here, that distance around there would be equal to 2 pi r. That would be all the way around, but we're only going 1/4 of the way around, okay? So that is going to be equal to pi times 200 divided by 2, which would be 314 meters. 314 meters, which would be our distance. Okay, and again, we are thinking of that as a straight line. And now we know displacement, we know our initial velocity, we know our time, and we can calculate our acceleration. Actually, I'm not sure if this is 5. Okay, so we're just going to ignore that. And we are going to determine what that acceleration is using kinematic equation number 4, which is going to be v final squared is equal to v initial squared plus 2a delta d, or the displacement. Our initial velocity is going to go away, and we are going to get 30 squared is equal to 2 times a times 314. So this is going to be 900 divided by 628, which is going to be probably about 1.35, I'm guessing. So 900 divided by 628, 1.43. Okay, so our tangential acceleration is going to be 1.43 meters per second squared. Okay, plus we have our 4.5. So now if we want to know our total acceleration, that's going to be the square root of 4.5 squared plus 1.43 squared square root. And we're going to get 4.7. So our total acceleration, the magnitude of our total acceleration is 4.7 meters per second squared. And if we kind of go back to here, once we get here, this right here is 1.5, and this part right here is 4.5. So if we want to measure that, if we want to measure this angle right here with respect to the radius, and remember, vectors can be taken off, so this is 1.5. So we're going to say inverse tangent of the opposite over adjacent. Inverse tangent of 1.43 over 4.5. And this was 1.43, not 1.5. So inverse tangent of 1.43 divided by 4.5, and that is going to give us 17.6. So we're just going to call that 18 degrees. Okay, and that would be with respect to the radius. Okay, so that is a follow-up to uniform circular motion and non-uniform circular motion. Non-uniform circular motion is going to give you any sort of curve that does not double back and make a circle. Okay. Now, obviously, if we had a constant centripetal acceleration, and that's all, then that radius would stay constant. And if that radius stays constant, it doesn't necessarily have to go all the way around. But that's what I mean by circular, as opposed to if you have a tangential acceleration, it's going to kind of continue to go. All right, so this is kind of the end of the centripetal and tangential acceleration, and a follow-up to week 4, lecture 1. Now, we're also going to do the last section, which is going to be on relative velocity, okay? And I'm going to give you kind of just continue on in this lecture about that. And so I am going to erase a couple things here, okay? Before we get there, we're going to talk about relative velocity. And we can talk about relative acceleration as well. But we're going to kind of concentrate on more of the relative velocity, which is actually pretty easy. Okay, now I'd like you guys to imagine yourself if you were on a bus. Okay, if you were on a bus sitting at the back of the bus. Okay, and let's draw a quick bus. Okay, and here is the seat, and you're sitting back there in the back of the bus, and the velocity of the bus is going to be, let's say, 10 meters per second. Okay, now that's relative to the road. That's relative to the road. Okay, and here you're going to stand up and you're going to walk if you were going to walk towards the front, and let's say that you were going to walk with a velocity that is equal to 2 meters per second, but this velocity, that velocity is relative to the bus, okay? So your frame of reference is the bus, and the bus's frame of reference is the road, okay? And so these two velocities are not being measured from the same point of view, okay, which is called a reference frame. And you can quickly kind of realize this. What is the velocity of you with respect to the bus? 2 meters per second, like we already said. What is your velocity with respect to the road? Now, since you're both moving, both moving forward, you're going to add your velocity and the bus's velocity together, and your velocity relative to the road, your velocity relative to the road would be 12 meters per second. And well, what if you got to the front of the bus and then you went back? And if you went to the back, then your velocity with respect to the bus is going to be -2, okay? And then if we were to then ask, when you were walking towards the back of the bus, what is your velocity relative to the road, okay? And then obviously it's going to be 10 minus 2, which would be 8 meters per second. Another way to think of this, which probably a fair number of you have been to airports in which they have a moving sidewalk to get you more quickly from one part of the airport to another. So if you have ever had two people, one is moving and walking on the movable sidewalk, okay, then they are going faster than they would have if they were not on it. So sometimes people would have a race with someone that is not on the moving sidewalk and someone that is. So obviously the person that is moving with the moving sidewalk would have an advantage. And also you might have done this where you are going to turn around and walk backwards. And if you were turning around and walking backwards on that movable sidewalk, then it would you could get to a position where you are standing still with respect to someone on the outside standing still, okay? Which means your velocity backwards would be equal to the velocity of the moving sidewalk going forward, okay? This happens all the time, and you guys are aware of that, even if you don't consciously think of it. So another common question here, and this is pretty easy because it's all in one dimension. Okay, well, if we do this in two dimensions, it is going to change things up, and it certainly becomes more complicated. But it's certainly within your realm of knowledge. Okay, and a very common way to explain this is if you think you are, let's say, even though we don't have such rivers in this area, if we had a river, okay, and let's say it is 50 meters wide, and it has a velocity of, let's say, 2 meters per second, 2 meters per second. This is the velocity of the river, okay, and it's going downstream, okay, let's say that you have a velocity, and then you can swim. So your velocity swimming is, let's say, 1.5 meters per second, okay, in still water, okay, and then you wanted to cross this river. Now, if you aimed straight across, okay, and kept your aim perpendicular to the shore, okay, how long would it take? How long would it take for you to cross this river? Okay, and this is a very simple equation, because we're going to have time is equal to distance divided by velocity, and we're going to have our distance of 50 meters, and our velocity is 1.5 meters per second. 1.5 meters per second. So 50 divided by 1.5 is going to be 33 seconds. Okay, so our time here is equal to 33 seconds. Okay. Now, many of you might be kind of thinking to yourself, it's like, you're not going straight across. You're not going straight across the river if you keep aiming straight across the river, which is certainly true. So even though you were aiming there, the stream, okay, the current of the stream is pushing you down. So how far downstream? How far downstream would you go? Okay. Well, now we are going to calculate the distance is equal to velocity times time. Now, this velocity is no longer your 1.5, it's the 2. And 2 times 33 is going to give you 66. So you will have gone down 66 meters, okay? And you will have crossed 50 meters, okay? So your overall distance, your straight line distance would be 50 squared plus 66 squared square root. You would have gone 83 meters. 83 meters. And your velocity would have been 1.5 squared plus 2 squared. And you would have had a velocity of 2.5 meters per second. So 2.5 meters per second would have been your actual velocity when you added those two things. Now, I want to point out, as long as you are still aiming, straight across the river, okay, then you can do that simple calculation of going distance divided by time, because the current is pulling you straight down. Okay, it's perpendicular to your motion, okay, your velocity, and therefore they are independent. Now, when they come together, it's not 1.5 and it's not 2. It becomes the 2.5 that you actually went, and you would have actually gone a farther distance. All right. So now let's calculate. If we could actually, can you swim so that you end up going straight across? Can you swim so that you end up going straight across? And let's check that out. And if you were going to swim straight across, okay, then you would be going, if you wanted to go straight upstream, then you would be heading at 1.5 meters per second, okay? But the current would have a velocity that's equal to 2 meters per second. 2 meters per second. So even if you went swimming straight up at 1.5 meters per second, the stream would bring you down at 2 meters per second, and therefore you could not cross straight across. Okay. Well, let's change this situation, And let's say now that the river has a velocity of only one, the current only has a velocity of 1 meter per second. So now you can swim faster than the current, and therefore you can angle, okay? You can angle up at a certain angle, which we will figure out, that will allow you to cross straight across. So now you are aiming upstream, but your actual path will be going straight across. Okay. Now, based on this situation, we want to find that angle. We want to find that angle. So again, we know that in still water, you can swim at 1.5 meters per second. 1.5 meters per second. And we know that the stream is got a new velocity of 1 meter per second. And now we can do a little trick. But now remember, this 1.5 is our hypotenuse, and our opposite side is going to be 1. Okay. And therefore, we are going to say the inverse sine of 1.0 over 1.5. And that is going to give us 1 divided by 1.5. That's going to give us an angle of 41.8. Okay, so let's just call that 42 degrees. 42 degrees. Now, that right there is with respect to the perpendicular to the shore. Okay, now we could give you this angle right here, which is 48 degrees. That would be 48 degrees with respect to the bank, So again, when we have angles like this, we need to qualify it based on our picture and based on what we're talking about. Now, if this was 42 degrees, then how fast would it take you to swim straight across? Well, now your actual velocity moving across the river is going to be the square root of 1.5 squared. 1.5 squared minus 1 squared. And you'd only be moving at 1.1. You'd only be moving. So your velocity with respect to crossing the river would be 1.1 meters per second. And again, if we still had 50 meters, we're going to have 50 meters divided by our velocity, 1.1. Okay. And 50 divided by 1.1, and that's 45 seconds. 45 seconds, which means that if you were going to swim slightly upstream, it would take you about 12 seconds. It would take you about 12 seconds longer to swim upstream, okay, than if you were to aim straight across. Remember, if you were to aim straight across, okay, you would end up going downstream, okay, and it would still take you 33 seconds to cross. Now, this change in current there means you would only go down 33 meters, and therefore you wouldn't go down as far. So that is kind of the gist of that relative velocity, and you will have some questions of the day, etc., to figure out this relative velocity sort of stuff. It's probably actually the easiest section of this chapter 4. And this will be the end. We're going to have a quiz on that this week, and we will then move on to chapter 5, which is on forces and Newton's laws. All right, we'll see you guys soon.